Hello students, in this video we are going to learn section 1.2 which is sequences. So first let me give you a formal definition. A sequence is a function such that the domain is a set of natural numbers. So this is a formal definition of a sequence. For example, you could have a sequence, let's say an order pair 1 4, an order pair 2 6, order pair 3 8, order pair 4 10, and so on. So this is called a sequence, but you can see that it is redundant to write a sequence as an order pair because the first term or the first component, this is always 1 2 3 4 and so on, right? So to make it shorter, so we can just make the notation cleaner. Just say that this is 4 6 8 10. That's it. So we understand the same way that the first term is 4, the second term is 6, the third term is 8. So we don't have to say, oh, 1 and 4, 2 and 6, 3 and 8. It's redundant. That is a lot better, right? To just make the notation shorter. Well, note that sometimes if the pattern is known, we can write a sequence as an explicit form. By this I mean you can say an equal to something. This is called an explicit form of a sequence. In this case, you could say an is equal to 2 plus 2n. Right, and then you can see that when you plug in n equal to 1, so you get a1 equal to 4, right? And that is your first term. And then when you plug in n equal to 2, so you have 2 plus 2 times 2, which is 6. That is the second term and so on. So most of the time, you're going to see a sequence in an explicit form like this. So an equal to something in terms of n. So let's do some examples. So let's take a look at example 4. So example 4 use the explicit formula for an to write the first 4 terms of each sequence. So we're gonna practice by looking at a formula of a sequence, and then we're gonna list 4 terms, and then after that we're gonna sketch the graph of the sequence. So the first one, we have a sub n equal to 1 over 2 to the n. So here I have a1 equal to 1 over 2 to the 1, which is 1/2. And then I have a2 equal to 1 over 2 square, which is 1 over 4. a3 equal to 1 over 2 cube, which is 1/8. And then a4 equal to 1 over 2 to the 4th power, which is 1 over 16, right? So this is the first 4 term of the sequence. You can say this is 1/2, a quarter, 1/8, 1/16, and so on. So if you want to graph this sequence, this is our n, this is our an. So the first term is going to be 1/2. Let's say this is 1/2. So the first term is here, right? And then the second term, this is a quarter, so it's here. The third term, this is 1/8, which is here. And then the fourth term, this is 1/16, which is here. All right, and that is the graph of the sequence a sub n. right? And so on. Actually, well, we just stop at 4 because, well, this is enough. All right, so let's look at example for part B. So let's suppose that I have a sub n equal to negative 1 to the n over n squared plus 1. So for here, I have a1 equal to negative 1 to the 1 over 1 squared plus 1, and that is negative 1 half. And then a2 equal to negative 1 square over 2 square plus 1. So this is 1 over 5, 1/5. And then a3, this is equal to negative 1 cube over 3 square plus 1. So this is negative 1/10. And then a4, this is negative 1 to the 4th power 4 square plus 1. So this is 1 over 17. So if you want to graph this thing, so let's make it both on positive side and negative side because we have negative number here. Alright, when n is equal to 1, so I have negative 1 half. So let's say this is negative 1 half. Alright, I plot it. And then when n equal to 2, so I have 1/5. Let's say this is 1/5 here. And then when n is equal to 3, so I have negative 1/10. So it just come back to the negative side, but it's just so close to the y-axis. Right? And then when n is equal to 4, so you have 1 over 17. So it's here, 1 over 17. Alright, to make it cleaner, I'm gonna delete 1, 2, 3, 4 here. Alright. And that is the graph of the sequence an. Alright, after you know the definition of the sequence, so now let's talk about the limit of a sequence. So let's take a look at the definition in the box. So if the term of a sequence an approach a unique number L as n go to infinity, then we say that the limit of an when n goes to infinity is equal to L, and the sequence converges to L. So basically, the limit of a sequence is the concept that we care a lot about the behavior of an when n gets bigger, bigger, and bigger. So like the last example that we have the graph of an like this. Like we have 1 over 2 to the n, let's say. And then you can see that the graph is like that, right? So what are we interested in is when n's go to infinity. So when n go to infinity, so this way, right? The one that I just draw the arrow sign here. So we want to know that the behavior of an goes to what? So in this case, you can see that you can expect that when n go to infinity, so an should converge to 0, right? Because the pattern of the graph is just getting close to y-axis, and it should be close to 0 at the end. So we're gonna say that the limit is equal to 0, and then the sequence an is convergent. This is what are we interested in about sequence. So basically the question that you're gonna see in this section is just check if the sequence is convergent or divergent. So in that case, you need to find the limit. So here I give you another term here. So if the sequence has no limit, we're gonna say that the sequence is divergent or the sequence diverge. So before we head to the example, because this is the concept of limit, so anything you learn from calculus 1, anything about limit, you can use it here. So let me review you something that it may be useful when you do the problems. So first of all, you can extend the domain from n to x and use the L'Hopital rule and just compute the limit as you did in calculus 1, right? Because if you extend the domain from n it's extend from the natural number to real number. So the behavior at the end will be the same. So it doesn't matter if you do it on natural number line or real line. So here, this paragraph is just to say that keep in mind that you can extend the domain to real number. Well, it will be useful when using L'Hopital rule. Well, I will point this thing out again when we do the problems. So you can read this thing by yourself. Another thing that you need to know is the law of limits. So the thing that we learned from calculus 1, you can use it here. For example, if you see limit of 1 over n to the r. So this thing must be 0, right? Because it is heavy in the bottom, right? This thing is heavy in the bottom, and on the numerator you have just 1. So limit of 1 over n to the r is always 0. And then you can use the sum of limit is equal to limit of the sum, and then you can pull out the constant. This is the limit law for the product, limit law for the division. So you can use it here. And also you can have the property of geometric sequence here. So if you see limit of r to the n here, this is going to 0 if absolute r less than 1. This is go to 1 if r equal to 1. And it does not exist when absolute r is bigger than 1. For example, if you see limit of n go to infinity of 1/2 to the n, something like this. So you can say this is 0 because your r is 1/2 and it's less than 1. Right? And then if you see limit when n go to infinity of, let's say, 35 to the n, so this is go to infinity, or you can say it does not exist because, well, number 35 is bigger than 1. Well, this is the review from calculus 1. And also you can use squeezing theorem if you want. So the squeezing theorem says that if you start from the inequality an less than or equal to bn less than or equal to cn, and you also know that the limit of an and cn is L, so it's gonna squeeze or force that the middle term must be L2, right? Because if your limit on the left term that you have is L, and limit of the right term that you have here is also L, then in the middle term limit must be L2. This is the statement of the squeezing theorem. So now let's do an example together. So example 5, this is similar to the question that you're gonna see on the exam. So example 5, find the limit of the following sequence and determine that the limit does not exist. So basically they ask you if the sequence is convergent or divergent, and if it's converged, can you find the limit? So the idea of this thing is super easy. So you can just compute the limit, and if the limit exists, so you conclude that the sequence is convergent. If the limit does not exist, you can say that the sequence is divergent. So first of all, we're gonna start by looking at 5a. So here we have an equal to n cubed over 3n cubed plus 5. So we're gonna just compute the limit of this thing. So limit of an when n approach infinity. So this is limit of n cubed over 3n cubed plus 5. So if you remember the technique from calculus 1, so when we see the limit as n go to infinity and I have the ratio of the polynomial like this, So what I usually do is I'm going to look at the highest power on the numerator and the highest power on the denominator, which is the third power here on the top and the third power here on the bottom. And then from here you can just divide it everything by n cube. So here I'm going to divide it everything by n cube. So I have n cube over n cube here on the top, and then I have 3n cube plus 5 over n cube in the bottom. So from here to here I just divided everything by n cube. This is a technique that you should use all the time when you see the ratio of the polynomial. And then after that you have limit n go to infinity. So on the top it cancel out to 1. In the denominator it's cancel out to 3 plus 5 over n cube, right? Because, well, you just simplify it. And then after that you can see that this term that I highlight in yellow, this thing go to 0 because you have 1 over n cube. And we just told you on the previous slide that if you see limit of 1 over n to the r, this thing go to 0. So this thing heavy is bottom, the bottom term is heavy, so this thing go to 0, right? And then, well, when you compute the limit, so you have 1 over 3 plus 0, and this is 1/3. All right, and then you can conclude that this sequence n cube over 3n cube plus 5, this is convergent and it's converge to 1/3. All right, that's example 5a. So now let's move to example 5b. So now let's look at the sequence n over e to the n plus 3n. So, well, we're gonna compute the limit, right? So limit of n go to infinity, n over e to the n plus 3n. All right, how do we compute this thing? So again, I saw n here and n here. So this is n to the 1 power, right? So we're gonna just divide everything by n. So we're gonna have limit n go to infinity. So I divided everything by n on the top, and I divided everything by n on the bottom. And then after that I have limit n go to infinity. So the top cancel out to 1, and then the bottom it's just e to the n over n plus 3, right? Because 3n over n cancel to 3. So the term that we have a problem is going to be e to the n over n here. This is a term that we have a problem because we don't know the limit yet, but other terms we have limit already. This is 1 and 3. So let's take a step back and think, what is limit of e to the n over n when n go to infinity? So if you look at this thing closely, you can see that this is an indeterminate form, infinity over infinity, right? From count 1, if you replace n equal to infinity into this function, so you have e to the infinity over infinity. So this is infinity over infinity. So we will extend the domain. We will extend the domain and use the L'Hopital rule. And use the L'Hopital's rule. So we're gonna compute limit of e to the x over x when x go to infinity. So when I say x here, it means I already extend the domain to real number. And then after that, I can compute it by using the L'Hopital rule. So I'm gonna say that, well, by using the L'Hopital rule, I'm gonna differentiate the top thing and differentiate the bottom thing. So this is e to the x over 1. Well, this is by just using the L'Hopital rule. So you differentiate e to the x, you get e to the x. You differentiate x, so you get 1. And then after that here, so you can say that, oh, now what we have left is just limit of x go to infinity of e to the x, which is plus infinity, right? Because e to the x go to infinity when x go to infinity. So here we conclude that. So the limit of e to the n over n when n go to infinity, this is equal to plus infinity, right? We did it by just using the help formula L'Hopital rule. So that means the term here that you have here, the one that I highlight in green is infinity. So this thing go to infinity, the one that I just circle now. This is go to infinity. So it does mean that it implies that the thing that we want to compute, which is limit of n over e to the n plus 3n, here, this is go to 1 over infinity plus 3, right? Because, well, we already computed the thing that I circled in red and then I got infinity. So the whole thing here that I highlight in yellow here, this is go to 1 over infinity plus 3. And that means the bottom is heavy, so this thing go to 0. Right? That's imply this thing go to 0 because it is 1 over infinity. So at the end, I conclude that this sequence n over e to the n plus 3n, this is convergent and it's converge to 0. Alright, let's move to example part C. So we have a sequence of cosine n over n squared plus n plus 1 plus 2 to the n over 5 to the n. So here we're gonna split into two pieces. So we're gonna start by completing the first term that I highlight in green first, and then after that we're gonna compute the limit of the term that I highlight in yellow, and then we're gonna add them up together. So let's start by looking at the limit of cosine n over n squared plus n plus 1 when n go to infinity. So how do I compute this thing? So first of all, let's recall that when you have cosine x, so the function of cosine x is like this, right? Yx, and then if you graph it, it's gonna be, this is a graph of cosine, and then you can see that as n go to infinity or as x go to infinity, well, the graph of cosine gonna be oscillating between -1 and 1, -1 and 1, right? So we have no limit for cosine x. So my idea, and this is what you should use, is when you see cosine, so you should start by thinking of squeezing theorem. So I will show you the technique here. So because the cosine is always bounded by -1 and 1, right? This is 1, this is -1. So cosine is always bounded by -1 and 1. So what we have here is we have cosine n is between -1 and 1, right? All the time. So because the value of cosine must be in between -1 and 1. And then after that, I am going to simplify until I get the term that is similar to what we want to compute the limit. So I'm going to divide everything by n squared plus n plus 1. Alright, so I do this on this inequality. So this is what we have. Looks good. And then after that, I compute the limit of the term on the left and compute the limit of the term on the right. And I hope that I will get the same number. And then by the squeezing theorem, I can conclude that the term in the middle is also have the same limit, right? So we're gonna compute limit of -1 over n squared plus n plus 1. This is the left term, and then if you compute this thing, you can see that the bottom is heavy again because it's gonna end up with negative 1 over infinity. So this thing is 0. And also we have limit n go to infinity of 1 over n squared plus n plus 1. This is also 0 as well. Bam! You can see that both sides that we have here, so their limits are 0, so we can just use the squeezing theorem. So by the squeeze theorem, the squeezing theorem or squeeze theorem, so we conclude that the limit of cosine n over n squared plus n plus 1, this is equal to 0 as well. So we are done with the first term that we highlight in green. So let's do the second term that I highlight in yellow here. So we have limit of 2 to the n over 5 to the n when n go to infinity. And this is super easy. I just need to simplify it. So I have limit of 2/5, right, raised to the n power. And this thing is a geometric sequence. So this is 0, right, because this is geometric sequence r equal to 2 over 5, right? And that thing is less than 1, so it means limit is equal to 0. So we already compute limits for both terms that I highlight in green and in yellow. So to sum up, so we have the sequence cosine n over n squared plus n plus 1 plus 2 to the n over 5 to the n. This thing is convergent and it's converged to 0, right? Because it is 0 and 0. So you add them up together, it is 0 as well. Alright, next we're gonna look at part D. Alright, this is the tough one. So let's look at it. So we have the sequence n plus 1 over n raised to the n power. So first of all, we need to compute limit of n go to infinity of n plus 1 over n to the n. Right, this is what we want to compute. And then you can see that this is an indeterminate form 1 over infinity, right? Because if you plug in infinity into this limit, so you're gonna get 1 over infinity. Interesting. So this is the form that you need to adjust a little bit and use the L'Hopital rule, if you remember from calculus 1. So we're gonna redo it again here. So I'm gonna let y to be n plus 1 over n to the n. And then now I'm going to take logarithm on both sides. So I have log y equal to log n plus 1 over n to the n, right? And then by the property of logarithm, I can just move n down. So I have n times log n plus 1 over n. Alright, and then after that, well, if I take limit on both sides, I have limit n go to infinity of log y equal to limit of n times log n plus 1 over n when n go to infinity. Alright, and then here what we have, if you replace n go to infinity here, so you have infinity times log of 1, which is 0, right? So this is going to be the indeterminate form 0 times infinity now. So if you remember from Cal 1, so if you face something like this, so you have to simplify until you get 0 over 0 or infinity over infinity. So what we trying to do here, we just move 1 over n down to the bottom. So I keep log n plus 1 over n on the top, and then I move n down to the bottom, so it must be 1 over n. Alright, so now it's come back to the indeterminate form 0 over 0, right? Because if you plug in n equal to infinity. So on the top you get 0, on the bottom 1 over n, so you get 0 as well. So now you're ready to use the L'Hopital rule, so you differentiate it. So use the L'Hopital rule. So assume that you extend the domain already. So before using your L'Hopital rule, you have to extend the domain first. And suppose that we expand the domain already, so we will n as a real number, and then we just use the L'Hopital rule. So we're gonna have limit n go to infinity of, so differentiate log of this thing, so differentiate log u, so you get 1 over u, right? So here you're gonna have 1 over n plus 1 over n. Well, let's make it cleaner. So we're gonna just take a step back and then just say that n plus 1 over n here. So I'm gonna say this is 1 plus 1 over n. So it's gonna be a lot easier to differentiate. So to differentiate log 1 plus 1 over n here, so I'm gonna get 1 over 1 plus 1 over n, right? And then I differentiate in the function, so I get 0, because differentiate 1 I get 0, and then differentiate 1 over n, so I get negative 1 over n squared. Alright, a bit tough, but it is doable. And then in the bottom here, so we have 1 over n, so if you differentiate 1 over n, so you get negative 1 over n squared. Alright, so after the long story, so we can cancel this thing out, right? Because they have the same term. And then after that, what you have left is limit of 1 over 1 plus 1 over n when n go to infinity. And this is just 1 over 1 plus 0, which is 1. And then after that, well, here to sum up, we have limit of log y equal to 1, right? And then once you swap the limit and logarithm, assume that you can do this. So this implies that, well, logarithm of limit of y, this is 1, and that is limit of y when n go to infinity. This is just e, right? Because logarithm of this thing is equal to 1. So that means the thing that I highlight in yellow here must be just e. So to sum up, so the sequence n plus 1 over n raised to the n power, so this is a convergent sequence and it's converged to e. Alright, and that is the end of this example. Let's move to another terminology of sequences. So in this slide, so we are going to learn increasing, decreasing, monotonic, and bounded sequences. So what you have seen in the box, this is a formal definition. So a sequence an is called increasing if an sub 1 is bigger than an. For example, 0, 1, 2, 3, 4, and so on. So the idea of increasing and decreasing function, they are super easy. So if you have a hard time to think of the notation, so you can just draw a picture. So let's suppose that you have an like this, right? 0, 1, 2, 3, 4. When you plot the graph, so you're gonna see that you have 0, 1, 2, 3, 4. For sure, this is increasing. Well, you can see it clearly after you draw a sketch of the graph. So if the question asks you to check if the sequence is increasing, decreasing, so you can just draw a graph. That is the best way to do it. So increasing is easy, so decreasing is easy. It's just another way, opposite of increasing, right? And then the word monotonic, this is the word that we use to describe either non-increasing or either non-decreasing. So in other words, it's moved in one direction. So that's mean monotonic. And then the last one is bounded sequence. So this may be new for you. So we're gonna say that the sequence is bounded if, so this is a typo, if there is a number m such that absolute an less than m. So bounded mean the sequence is just bounded by some number m. So you will see it in the picture. For example, let's say that you have the graph of cosine and sine, right? This is the standard way to do it, standard way to memorize it. Let's say that you have 1, -1, 1, -1, 1, -1 here. So you can say that this sequence is bounded, right? Because it's gonna be always swap between -1, 1, -1, and 1, -1, and 1. So it's bounded by 1. So it's bounded by some number. That is the idea of the bounded sequence. So let's do an example together so you see the idea of this thing more deeply. So example 6, for the following sequence, so answer the following question. Is the sequence bounded? Is the sequence monotonic? So let's do it. So the first one is n squared plus 1. So as I told you, if you have a hard time to think about this thing, so you can draw the graph first. So what is the graph of n squared plus 1 here? So when n is equal to 1, so you have a1 is equal to 1 squared plus 1, which is 2. All right, let's say this is 2. And then a2, this is 2 squared plus 1. So this is 5. So it's getting bigger. So a3 is equal to 3 squared plus 1. So this is 10. So it's a lot bigger. All right, from here, you can see that, well, the sequence n squared plus 1, this is not bounded, right? Because as you go more and more, n is getting bigger and bigger and bigger, so you can see that the an goes to infinity as well. So n squared plus 1 is not bounded, because if it is bounded, it must be some number m that keep the value of the sequence below that point, but this is not bounded at all. So another question is it monotonic? So we say that n squared plus 1 is monotonic, right? Because clearly this sequence is increasing, so it must be monotonic. So this match with your intuition, because monotonic mean monotone, right? So increasing mean monotone, right? Because it just keep going in one direction. All right, let's look at part B. So this example is 7 minus 1 half to the n. So let's plot the graph. So a sub n and then n here. So the first term is, let's say when n equal to 1, so you get 7 minus 1 half. So actually I'm gonna do 7 here. I'm gonna plot 7 minus 1 half, which is 6.5. All right, that is the first term. And then the second term when n is equal to 2, so this is 7 minus 1 over 4. So this is 6.75. 6.75. And then when n is equal to 3, so it's just getting close to 7, right? So after you plot, you can see that, well, the behavior of the point here is going to be close to 7, right? As n getting bigger and bigger and bigger, so 1 over 2 to the n goes to 0, and then the graph is just getting close to 7, but it will not touch 7, right? So to sum up this thing, so we have 7 minus 1 over 2n. This is bounded. You can say this is bounded by 7, right? Because it's gonna you have the line y equal to 7 here to cap your sequence, so the value of an will not exceed 7. And then also you have 7 minus 1/2 to the n. This is monotonic as well because it's go in one direction. All right, the last one I have cosine square n pi over 2 here. So we have to manipulate this thing first. So a1 is what? So it's cosine square n, which is 1, right? So it is cosine square pi over 2. So this thing is 0. So a2 is cosine square 2 pi over 2, which is cosine square pi. Well, this is 1. And then a3, this is cosine square of 3 pi over 2. All right, this is also 0. And then a4, this is cosine square 4 pi over 2. So this is cosine square of 2 pi, which is 1. So actually the sequence is going to be 0, 1, 0, 1, 0, 1, 0, 1, and so on. Alright, so this thing cosine square n pi over 2. Well, clearly this is bounded because it's bounded by 1, right? Because the value you're going to swap between 0, 1, 0, 1, 0, 1, so it's bounded by 1. And then also this sequence, is it monotonic? So the answer, this is not monotonic because it does not go in one direction. It's going to swap between 0 and 1, 0 and 1 all the time. So if you plot this thing, so you can see that what you get is going to be at 1, this is 0, and then 1, 0, 1, 0, 1. It is bounded, but it is not monotonic. Now let's look at an application of this topic in real life. So the bounded monotonic sequence theorem says that a bounded monotonic sequence converge. So as long as you have a sequence that is bounded and monotonic, it is always convergent by this theorem. So the example here that I just quoted for you, you can read it by yourself, but I am looking at the temperature of the coffee. So, well, let's suppose that you have a hot coffee in your hand and then you spill it. So, at the time t equal to 1, so t1, this is, maybe you can think of the first minute that you spill the coffee on the table. So you can see that the temperature gonna be cool down by the time, and then after that, at some point when n go to infinity, the temperature is coffee is going to be stable, and that's it. And that means the temperature is convergent. So we are not going to test you a lot on this thing, but this is fun to read. So just keep in mind that there exists a theorem like this in real world too. To wrap up this section, we're gonna do example 7 together. So let's determine whether the following statements are true and give an explanation or give a counterexample. So it means this is true or false question. So let's start by part A. So if the sequence an converges to 1 and if the sequence bn converges to 3, then we can conclude that the sequence an over bn converges to 1/3. Is it true? So you have limit, right, of an when n go to infinity equal to 1, because the question said that the sequence of an converges to 1. And then you have this, which means limit of bn when n go to infinity equal to 3. So can you conclude that the sequence an over bn converges to 1/3? The answer is yes, right? So this statement is true, because once you compute limit of an over bn, right? This must be 1/3 by the limit theorem. That's it. All right, part B. The sequence an converge to 0. So what we have here is limit of an when n go to infinity is 0, and limit of bn is what? So the question said that the sequence bn diverge. So limit of bn when n go to infinity, this is plus infinity. All right, and then the question asks you, can we conclude that the sequence an and an times bn converge to 0? So is it true that limit of an times bn, this is 0? So the answer is what? It is false, right? Because when you have the limit of an is 0 and limit of bn is infinity, so then limit of an times bn, this is an indeterminate form, 0 times infinity, right? This is what we learned from Cal 1. So we still cannot conclude anything from here, right? Because it is an indeterminate form. It could be 0, it could be 1, could be 2, could be anything. Well, we have to simplify and apply the L'Hopital rule. So this question, the answer is false, and the reason is here. All right. So if you want to give a counterexample, you can take an to be 1 over n, right? And you can take bn to be n. So here you can see that the limit of 1 over n is 0. The limit of n is infinity. And when you compute limit of an times bn, right, this is the limit of 1 over n times n, which is the limit of 1, which is 1. So this is not equal to 0. So this is your counter example for part B. All right, let's move to part C. So if the sequence an converge, then can we conclude that the sequence 0.00001 an converge? So here, if you know that limit of an when n go to infinity converge, well, let's say convergent, and the limit is L, then can we say that limit of 0.00001 an exists as well? So the answer is yes, right? Because this is just constant. So you can just pull this thing out. And then that is the 0.0001 times limit of an. This is 0.00001 times L. So limit exists, right? Because this is a real number as well. So this statement is true. So that means, the sequence 0.00001 an is also convergent as well. So let's look at the last question here. So there is an example of a convergent sequence that is bounded and monotonic. So convergent sequence that is bounded and not monotonic. So can you find that? So let's draw a picture. So we need a sequence that is bounded and also not monotonic. So let's start by looking at not monotonic first. So we want a sequence that is not monotonic. So we are going to start by maybe just use the concept of sine and cosine. So let's say that this is my n. So I'm gonna start by this and this and this and this and this and this and this. Let's say this is 1 and this is -1. So this is not monotonic already. And then we want a sequence that is bounded. Yes, it is bounded by 1 now, right? You can say that. However, the sequence here, this is not convergent, right? Because when n go to infinity, it's going to be swapped between -1 and 1, -1 and 1 all the time. So we just need to fix it a little bit. So we are going to change our term here. So instead of doing a swap between -1 and 1, so we're gonna do 1 here, and then we're gonna do something that has less magnitude here, and then something less magnitude here, less magnitude here, less magnitude here, and so on. So it's guaranteed that this thing go to 0, right? Well, that is a lot better, right? So this thing go to 0 as n go to infinity. So the answer here is yes or true. So that is an example. So the example is, so an example is, let's say you can have -1 to the n plus 1 over n, for example. If you try this thing, so you can see that the picture is going to be the same at this picture, and then, well, this is an example of a convergent sequence, because you can see from the picture that it's go to 0 when n go to infinity, and also bounded and not monotonic. So example 7 here, this is a conceptual question. This is a hard question.